model given here. Assume for a moment that the true error variance is known, that is, the error variance for each observation is known. So meaning that error variance depends on I, the position, the order on observation. So what we can do, we can transform the equation by dividing the equation with the square of the variance. Okay, this one sigma divided by sigma I. The known value if we know. So this is just theoretical because we most of the time we don't know. So later we use the case of unknown when the error variance is unknown. So if we know the value, for example, all we have done here is to divide or deflate both the left and right hand side of the regression equation by the known sigma I, which is simply the square root of the variance sigma I squared. So now let the transform equation, this one, this is a new error term after we divide the equation. So we have a new error term which is we rename as Bi equal to this one. So recall the Bi, the transform error term. If the Bi was homoscedastic, then the transform. So if they say after we transform, we are able to make this to be homoscedastic, then okay, that's mean that we need to transform the equation so that the new error term, the error variance of the new error term to be, or the new disturbance to be homoscedastic. Okay, so the Ui is homoscedastic because error variance depends on I. So we need to transform the equation so that the new error, the new disturbance has homoscedastic error variance. So if Bi homoscedastic, then the transform regression does not suffer from the problem of heteroscedasticity. It's not too difficult to show that the error term Bi is homoscedastic for this example. Since Bi equal to this one, the new error term Ui over sigma I, then the square of this, we get the square of this one. Therefore, the expected value of the new error Vi square, expected value is the variance of the new error is given by this. Okay, because we know that so this one square, so we know that this one, so this one can be taken out. So we already have this one. So the variance of the Ui is sigma I square. Okay, the original model, the variance of the disturbance in the original model is sigma I square, which that depends on I. It depends on I. So different I has different value of variance. So if you transform the attachment, meaning that the error variance for the new disturbance, the transform equation is equal to 1. So which is a constant. So which is obviously a constant. So the transform error term Bi is homoscedastic. As a result, the transform regression model does not suffer from the heteroscedastic problem, and therefore it can be estimated by the usual ordinary squared method. The ordinary square estimators of beta 1 and beta 0 and beta 1 obtained are called weighted least square or WLS estimators. Each y and x observation is weighted, that is divided by its own heteroscedastic standard deviation sigma I. Now, I mentioned just now, we do not know the value. Okay, the true value of error variance, then we have alternative way for the case of unknown sigma I square or unknown error variance. Despite its intuitive simplicity, the weighted least square method requires us to know the true error variance sigma I square. Unfortunately, the knowledge of the true error variance is a rarity. In the absence of knowledge about the true sigma I square, the error variance, we could consider alternative approaches. So there are two possible cases. The first case, if the error variance is proportional to any of the x. Okay, meaning that you have any x, then it's proportional to any of x. So for example, just now, if let's say you have many variables, let's say your dependent variable is consumption, and then you have many variables, and one of them is income, then maybe the income is the source of problem. That variable that produces the heteroscedastic error variance. So proportional to that particular x. Case 2, if the error variance is proportional to x squared. So we have a slightly different way of transforming or using vector square equation to overcome or to remedy the problems of heteroscedastic error variance. So case 1, the error variance is proportional to xi. So different xi has different variance. If after estimating the usual on the least square regression, we plot the residual against the experimental variable x and observe a pattern that indicates that the error variance is linearly related or proportional to xi. That is, the error variance is one expected value of u, expected value of ui squared is the variance, not the variance of ui. The variance of ui is equal to sigma square xi. So it depends on the value of x. So it's proportional to x. The variance of u, the other term is proportional is sigma square times xi is proportional to x, which state that the heteroscedastic variance is proportional or linearly related to xi. So given the assumption that the error variance is proportional to xi, we need to transform the model as follows. So if we believe that the error variance is proportional to x, then you have to transform the equation by dividing each of the variable with the square of that particular x. Just now I mentioned that if you have 3x, let's say your y is consumption, your x you have 3x, and one of x is the income. And then because of that consumption and income, just like the example before, okay, higher income will produce higher spread of error. And then when they say x2, x2 is that consumption, then you divide by the square of x2. Okay, so you have beta 0 plus beta 1 x1 divided by square root of x2, and then you have another variable beta 2 x2 divided by square root of x2 as well. Understand? This is an example when you have one x, but you have more than one x, you have to divide the square root of that x that produce the problem. Again. So this one, they intercept, originally intercept the 0, so you divide by. So it's just like we have a new variable, it's just like we have a new independent variable. So 1 over the square root of that particular x. And then you have this one, xi over square root of x, so it's just the square root of x. And then this one, it becomes a new disturbance, new error. Okay, new error term, which is equal to this one. So where vi, a new error, is equal to this one, that is, we divide both sides of the model by the square root of xi. So that is this one, we divide model by the square root of xi. So it can be proved easily that the error variance vi in the transform regression is homoscedastic, and therefore we can estimate the transform model using the ordinary square. So the reason for us to transform, so that we want the new error term to have homoscedastic error variance, no longer heteroscedastic. So this one, previously ui is proportional. I mentioned before, the variance of ui is proportional to x sigma square xi. But now after we transform, so we hope that by transforming the equation like this, we are able to make a new error to have equal spread of error, to have the what we call it, the homoscedastic error variance. So you look at the proof given here. So this one, so we know that the error variance proportional sigma square xy proportional to x, and then when we after we use the quadratic square transformation, the new error in the new equation has equal to this one, is equal to this one. So if the variance of this is equal to this one, the variance of this is just this one square, so square is one, you only have and then you take out, so 1 over xi. So we know that this part is the variance of the original error, ui squared is the sigma squared xi. So if you cancel out this one, then you will have sigma squared. So meaning that we transform the equation so that the new error term does not the error variance is just sigma squared, it does not depend on I anymore. It does not depend on proportional to x. Okay. So it is important to note that to estimate the transform regression model, we must use the regression through the origin estimating procedure. Now, because in the equation just now, the one that originally as intercept, now it becomes a new independent variable. Okay, so we don't have intercept anymore. So this one we have we say that it is through the origin estimating procedure. So go back to your previews. This is the original data. So how, if let's say after, for example, you inspect the residual against x and you see there is possibility that you can see that when sales increase, the R&D sales increase, then the residual, the size of the spread of residual also increase, then meaning that there is possibility that the error variance proportional to sales. Then if that is the case, then what we can do to remedy the problem. So what we can try to do, using the first option, if we believe it's proportional to x, then we divide by the square root of x. So this one, let's say we keep this one, we estimate model. So quick estimate equation. So again, quick estimate equation. Now we want to estimate the weighted least square regression by assuming that the possibility, the error variance of this, which is heteroscedastic. So we want to overcome the problem. We try to use the weighted least square. So we re-estimate RDEXP divided by a square root of. So because this one we only have one independent variable, we know the problem is sales. I mentioned before, if you have more than one, as you have 2 or 3 x independent variable, you have to identify which one first. For example, by looking at the graph of the residual against each of x. Okay. Or you also consider the nature of the variable. You believe which is actually the most likely to be the source of problems. Just like income consumption income. So we know the higher income have more variation in the way that they consume. Okay. So SQR square root of sales. So originally as C, now it becomes 1 over square root of sales. So we no longer have C, so 1 over SQR square root of sales. And then our sales divided by square root of sales, so it becomes square root of sales. SQR. So this one you understand, maths. Okay. The sales divided by square root of sales is the square root of sales. So okay. So we get this. It is same that we check -235. So I mentioned before, the original estimate is okay, you can use one, but the problem is here. The problem is our standard error. So that's the statistic period also not reliable anymore when we have heteroscedasticity problem. So we need to remedy so that we have a reliable estimate of standard error, t-safety and value. But this one still significant significant. But there is a case that when you with heteroscedasticity and without that, the significance is not the same. Okay. So that's why we need to lessen the influence of the effect of heteroscedasticity so that we are reliable. So increasing the chance for us to make correct conclusion when you perform hypothesis testing. So this one, if you want to test whether we already lessen the problem or solve or remedy the problem, you can perform the test as before. So view, for example, residual, heteroscedasticity, let's say we just use the brush product calculate. Now it is greater than 0.05. Okay lah. Yeah. So anyway, you can make conclusion based on for the significance of variable, the significance of sales, the influence of sales on R&D expenditure based on the result of this one, the testing and the p-value. So don't make conclusion based on this because it's not reliable. So you conclude based on the testing, performance testing based on this. So the estimate of slope not much different. 0.308, 0.036, the one original 0.0. I mean the intercept much different, but the slope, the way that you interpret is not much different. Okay, so when the sales increase 1 unit, then R&D expenditure increase by 0.036 unit. So either one or so this one. Okay, and then if let's say you try the first case but still unable to solve remedy, you still fail the test, and then you can try this one another assumption that the error variance is proportional to x squared. So if the estimated residual show a pattern that proportional to x squared, we suggest that the error variance is not linearly related to x, but increases proportional to the square of x. So meaning that the variance of u, the variance of the term, is sigma square x square I, not x but x square. So it's proportional to the square of x. Okay. So in this case, the appropriate transformation is to divide both sides of the model by xi rather than by square root by the square root of xi. So you divide by x, not the square root. Okay. So just like before, you have more than one x. First, we have to identify which x first, and then you divide by the x. Or the whole equation divide by that particular x. So don't only divide by that particular x. Do not mix. Let's say this one you divide by x1, this one you divide by x2. Okay, you have to divide the same x. Yeah. So you will see the example, divide by y, divide by x, and then the constant become new independent variable 1 over x, and then this one xi over xi, so 1. So this equal to 1. Remember, in 1 it's just like your x matrix. If all equal to 1, then it's just the intercept. So now this one just like become a new intercept, and then this one is the new disturbance, the error term. So similarly, we can verify easily that the error term bi is homoscedastic, and so you refer to this one, the second one. So if x proportional, the error variance proportional to x squared, like this, and then we divide by x, so that is the new error, and then the variance of this new error given by this. So if we take out this one out, and then this one, the variance of this. So we cancel out this one, cancel, so we have sigma. Okay, so originally, which is dependent on I, now it's no longer dependent on I. So this one is homoscedastic. Okay. So an interesting feature is that what was originally the slope coefficient now become the intercept, and what was originally the intercept now become the slope coefficient. So this one originally intercept, now it become slope for this variable, and then this one originally is slope become intercept. So this change, however, is only for estimation. Once we estimate the transform model, multiplying by xi on both sides, we get back to the original model. Okay, so again this one, if let's say you are able, after you perform the test, still fail the test, so meaning that it failed to remedy the problem, so you can try another option by assuming that error bar proportional to x squared, so you divide by x. So this one is the square root, yes, still, and then this one. This one 6 over 6, just 1. Originally 6, huh? 6 divided by 6 is just 1. 1, so we got intercept, now we go see. Okay, so what originally is intercept now become new variable. What originally as loop now become intercept. Okay, so you get this one. So you can test again whether this is reliable for us to perform type testing or not. You check lah. So let's say you just test using the first one, what problem of rate, and this is p value 0.22. That's acceptable. Okay, so it's acceptable. So you can. It's more safer to make conclusion about the significance of the influence of cells on RNA expenditure based on this p value. Okay, then the original one. But original one for this example hope significant. So, but it's possible that for other cases, that the significance is not the same. Meaning that maybe the original one is not significant, but after you remedy is significant, for example. So other possible method is through re-specification of the model. So instead of speculating about error variance, sometimes a re-specification choosing a different functional form can reduce heteroscedasticity. For example, instead of running the linear invariable regression, if we estimate the model in log form, it often reduces heteroscedasticity. That is, if we estimate, so you use log transform value of y and regress against log transform of x. And you have to rely on the one that you already remedied for, after you remedied for. So without the heteroscedasticity, otherwise it's not reliable. Okay. So log transformation compress the scale in which the variables are measured, thereby reducing a temporal difference between two values to 4, so that you reduce the size of the magnitude of the values. So as an example, the number of 90 is 10 times the number of number 9, but log 90 now is equal to 4 something, so only about 2 times as large as 9, log 9 equal to 2, so meaning that the difference is going to be, so let's say just now like we have consumption and income. So when you transform using log of income, so meaning that the difference is going to be smaller from the smallest, for those has the value of income for low income group and income for higher income group, the value, the number is going to be not too large. Okay, that can help to reduce the chance of having heteroscedastic or heteroscedastic error variance. Okay, using log. So for the model just now, instead of to overcome this one, instead of using weighted least square, you use log. log of RDEXP regress log again, okay, have C lah, intercept, and then log of sales. But if you use this one, remember the way you interpret, you have to interpret as percent, electricity. Okay. And prediction made, prediction for the log, not prediction of the original value, prediction of log of R&D expenditure. Your y hat fitted value. Okay. So, is this reliable for us to make conclusion or to make inference? Then you can check, you perform the test. Let's say I just use the first one. So using the first one now, it is p value 0 greater than 105, so you conclude there is no heteroscedasticity. So the original one, it failed the problem perfect test, but now after we use block model, now it passed the test. Yeah. So it is able to conclude the significance of, but this one the inverse of log of sales it is significant. So this one also significant, but this one you will just break the risk of making incorrect conclusion. Okay, if you do not remedy the problem, because this has the problem of it has heteroscedastic error variance. This one has homoscedastic error variance. And then another option to redefine variables. Regress per capita dependent variable against per capita independent variable. For example, in the study of expenditure on travel and the corresponding income for 51 cities or countries, we might expect that the error variances are heteroscedastic and increase with population size. So cities or countries with large population are likely to have greater variation in expenditure on travel than small. So you are using data like this, then instead of using, let's say you use the what we call the number of expenditure, for example, expenditure, because expenditure for large country has larger expenditure. Let's say country with large expenditure on certain thing by US compared to Malaysia. Of course, you have larger responsibility. You have data for different countries, for different cities, and then you use the data that represent the total volume for each of country or each city. Then there is possibility for you to have the problem now, because large value, large country will have larger size of error. We produce the larger spread of error, so they have larger error variance. So it depends on the country or depends on cities. So in order to overcome the problem, instead of using original value, you divide and take average. So per capita means what? Per capita you divide by size of population. So let's say you have expenditures, or let's say consumption, the total consumption or fuel consumption in US divided by population US, and then total consumption in Malaysia divided by population in Malaysia. So you have what we call that average per person for all countries. Okay, for all countries. So that you don't have larger value and then small value. So now all countries will have quite not that much difference, because average per person. Okay, average value per person in that country. So use per capita. And then last one is the use of reverse standard error. So why heteroscedasticity corrected standard error, as we have noted in the present of heteroscedasticity, the honorary square estimated, although unbiased, are inefficient As a result, the conventionally computed standard errors and t-safety of the estimators are suspect. What has developed an estimating procedure that produces an error of estimated regression confidence that takes into account heteroscedasticity. As a result, we can continue to use the T and F tests, except that they are now valid asymptotically. Theoretically, there is a large sample. You have to remember, if you want to use this one requirement is that the size of sample must be large. Okay, so there is no what we call it. There is no clear guide on how many, the size, what is the required sample size. So, but for small sample, you should not use now. You definitely can use this for small sample. I say just now we have example. We have 18. It's quite small, so you cannot use. But later I will try to show. I just show you how you have to use that one. But if you have small sample like this, 18, then don't use this one. So if you have, my suggestion is that if you have less than 50 observation sample size, do not use this. But even 50 also sometimes not sufficient. It depends on the seriousness of, if let's say the error variance 2 depends on X seriously, and then maybe you need higher sample size, larger sample size. Okay. So this approach, this one is advisable to present the usual standard errors as well as wide heterogeneity corrected standard errors for comparative purpose. But keep in mind that wide methodology is strictly speaking applicable in large sample. So if you have very large sample, then for example you have sample size 1000, for example, then you can confidently use this one. But if you have only 50 or less than 100, so meaning the next possibility that it's able to have to remedy, but it's also possibility that it is not able to have to remedy, totally remove the heteroscedastic error. So you have to be careful. So this one, if you read the notes given, so the robust standard error, it corrects the estimate of standard error. So it is robust from the influence of heteroscedastic error variance, but it does not have influence. It does not change the estimate of the parameters. Because we know that parameters still unbiased. Okay, the estimator of parameters still unbiased, but the problem is with standard error. So basically, we have a number of way of estimation for the error variance or standard error, so that it helps to reduce the effect of heteroscedasticity. So for the case of if we have heteroscedasticity, then we can use this one. The heteroscedastic consistent covariance estimate or the y. He will y later on. So I show you. So this one, if let's say for the given example, this one, so we have RDEXP, the original model, this one. But now you have problem here, right? If let's say our sample size is large enough, then you have an option to use that one. To use that option to estimate robust standard error, you go to estimate, you go to option, you select Q by Y for the. Okay. But this one, it will not have, if you're unable, it's actually not suitable to be used for this data because we have small sample. This one I just show the stat. Okay, I just show the stat. Later maybe you will find other sample data that will larger sample size. Okay, so you just estimate as usual the same equation, the same. But when you go to options, like instead of ordinary, you use this one. You go Y, and okay. So it gives you. The estimate of the confusion is still exactly the same. So it just correct the estimate of standard error. But this one still not reliable because we have small sample. So I don't think this one, what we call it, able to help to the same problem. So this one you cannot test this before because the estimate of the confusion is still the same. you cannot estimate, you cannot check from by testing this one. If you test this one, it still show the result of the original one, still like before. So you cannot, you cannot check whether it is already this approach able to remedy the problem or not. One possible way, if you want to see whether the use of this approach able to remedy problem is by comparing with the other method. For example, you use the proportional to x, proportional to x squared, to take a square, for example. And you compare this one is significant, whether it is same or not, whether this is safe or not to be to conclude based on this. Okay. So that one way now you have, but this one you have to remember that this is useful only for the case of large sample size. You have small sample size, then don't do this. Don't use it. Use other method. Okay. So you can use the other method using log, for example. If you use double log model, you can check. After you extend model, you can check and you can perform the test. Okay, let's quickly do the lab session 6. Five. So for question number 1 is quite, number 2 is quite similar data, but we will do quickly to the example given in the notes. For question, last question we have example of 2. We have two variables in model. So the first question, what is meant by heterocharacteristic? What are its effects on the following: on the square, estimated and their variances, then confidence interval, and the use of T and F tests of significance. Heteroscedasticity means that the variance of the error term in the regression model does not remain constant between observations. So different observation has different size of variance. The ordinary square estimated are still unbiased, but they are no longer efficient. So the estimate still can be used, but it is no longer efficient. Means that because the variance become larger, so the possibility of it to get estimate far. Although the average still unbiased, okay, but the possibility, the chance for you to get the estimate far from the true value is higher. So since the estimated standard error on the square estimator may be biased, the resulting T ratio are likely to be biased too. As a result, the usual confidence interval, half the testing procedure, and etc. are likely to be of questionable value. So the half testing cannot be done correctly, or maybe we cannot trust it, okay, in the result. So number 2. So now we have our integration, but we have profit another independent variable. So estimate the regression model, obtain residual, and plot. Do you take any? Plot against an variable. So this one, if you estimate the model, so Q2 actually. So our dependent variable R&D EXP before, and then profit. Our dependent variable. Okay. So if you go to actual fitted residual graph, so you can see now this one the residual, this one the residual is getting the spread of the error residual getting bigger. How to get this one? So after you estimate this one, you go to view, actual fitted residual graph. Okay, so you see, right, this is the actual, the red line, and then y hat is given by the green line. So the blue line represents your error or residual, y minus y hat. So you see, for small value of x profit, for small value of profit, we have small spread of error residual, but then for higher value of profit, we have larger spread of residual. So it indicates that the error variance depends on the value of profit. So higher profit has higher variance. Okay. So if you produce plot, how to detect the problem? If you have more than one variable, then you need to plot one by one. So you have residual. Residual is one residual. So you have here. See, if you produce plot, scatter plot. So if you press Ctrl and choose profit and receipt. And then you right click your mouse, open as group, and then you graph select character. Okay, so you see this one. So as profit increase, spread out just like this one, quite similar, right? Yeah. So there seems to be some evidence of heteroscedasticity in the model. C. Verify your qualitative composition partly with a bit of graphic, having a test. So you perform a test. So this one, the model that you estimate. So perform the fourth test. I will not do the manual one. So manual one you can do later at home. So here we just use the original model. Okay. So you perform the test, review, residual diagnostic, heteroscedasticity. So perform each of the tests by Pagan. What else? Ledger, one by one. So okay. Pagan. So you fail the test because p value. I mean you can conclude based on this also okay lah. But this one to be constant with the manual one, then we can use one. So p value less than 0.05, so we reject. We conclude that there is heteroscedastic error variant. You perform using other test, the ledger test. Residual, heteroscedasticity, this one. So the same conclusion. And then the third one is how they view residual diagnostic, heteroscedasticity test, how they also the same. So previously for the earlier example, this test it passed the test, meaning that based on the Harvey test says that there is no heteroscedasticity, but this one has, all the three tests has heteroscedasticity. And the other one is arch. To view arch test. Okay, now we do have problem. So this result of estimation is not that reliable for you to make conclusion regarding the significance of the influence of profit on R&D expenditure. So you have to remedy first before you can confidently make conclusion of for the hypothesis testing. So now, if let's say we assume we try the assumption that the error variance proportional, this one proportional to x, but whether x or x squared. You see, as x increase, the spread increase, right? You see the graph, you see the picture, scatter plot. This one, as the value of profit increase, the spread of residual also become larger. So it's proportional to x. Whether proportional to x or x squared, we're not really sure lah. So you can try. Okay, so let's say proportional to x, we have to maybe this one we for comparison you keep this one, you close and name as equation 1, name equation 1, and then you estimate another one. So this is original one. So now if using weighted square, so we divide REXP over square root of profit. And then originally C becomes 1 over square root of profit. And profit over square root of profit is square root of profit. Okay. So this one after, so this one you can check again, perform the Prashpragan corporate test. So this one 0.30 means that still has a problem lah. So this one but slightly better in terms of p-value. I think this one p-value smaller, right? Before. This one Prashpragan much smaller than this. So to some extent it have to lessen, but still have a problem. Okay. So we can try another option by assuming that error varying proportional to x squared. If proportional to x squared, we divide by profit, not square profit, but profit. Profit. So originally as an intercept now become 1 over profit. And then profit over profit 1, which is equivalent to have an intercept C. Okay, so you get estimate. So can we use this as compared to this? The estimate just like different, but now you have a different XE. So you perform the test again, residual, heteroscedasticity, and then it's okay lah. 0.4. Then it is much safer to conclude based on this. Although the result still not significant, not significant. But again, there is possibility for other case, you can get different conclusion. Original, for example, not significant, and then when you remedy it's significant or otherwise. Question number 3. Use log transformation so use double log model. Okay, this one you can try your own. This one I will not show you. You have to split just like before. So this one I just show you. We perform the using log and then the test using the test that we discussed before. Okay, so if you use log, then log of Okay. So this one, can we conclude that log of profit has significant influence on log of opportunity? Can you perform a test? And okay, this one. So very good. This one 0.9. Okay. So there is no heteroscedastic using double log model. So this one, because number of sample size small, 18, so don't use the robust error. Question number last one. 4. Consider the following model regressions. We have 2x. So LE is the life expectancy in years. And then we have two dependent variable, income and assess. Income per capita income US dollar. Assess and index of assess of health care. So using variable given in the use an estimate model. So we close this one first. Close. And your data given here is number 4. So estimate model, create estimate equation. So we have LE, our dependent variable, and then space C for intercept, income, space assess. So use white test. So you estimate and then test the present of heterogeneity by conducting a white test. So you go to view, residual diagnostic, heteroscedasticity, select white. Okay, select white and then we conclude. So based on white test, suggests that the model has heteroscedastic error variance because p value smaller than 0.05. So if you want to perform the test manually, for this one, for example, because previously we only have one x, so we first need to estimate and get residual. And then you need to regress residual against, so you estimate, this one I say first, equation 1. So, and then we estimate the residual against, well, I think this one for the white test is square residual, right? So, square residual square. And then we need to have include all x, so we have income and assess, and then we have square each of x, so income square, we have assess square, and interaction, income and assess. This is how many way we perform the white test. Okay, the minimum V. So you estimate this and then you get R and you multiply N times R squared and then you should be able to get the same, the one I produced. So this one, N 85 times R squared, you should get the same like here. Okay. But if you do this, then you don't have p value, right? You compare with the critical value from table. So let's say now you get an exam, for example, an exam. You are given the result of this, you don't given this, you are given this, and then you have to know how to calculate. So this times this, and then you compare critical value from chi-square table. Okay, but for the midterm test, because it's conducted here, use then just use the easy way. This one, don't do the manual. Use this one. You want to use manual, up to you. Okay, use the easiest way to do this. Okay. So now, how to remedy the problem? So we have a number of different ways we can use, but if you inspect the residual against excess, the graph, plot of graph, you produce plot of residual against excess and residual against income, you will not be able to see it is proportional to x, any of x. So you cannot use the vertex square. Actually, you can try it on at home, but if you try using vertex square, it's unable. They say you believe that excess is a problem. They say you believe excess is a problem, so you have to divide this one over square root of excess, each of these. But it doesn't work because it is not proportional to x. So not all methods will be able to solve the problem. So you have to find other solution. For example, use double log model. You can try double log model. So in double log model, you add log. Okay, so we get this. So, and then you check, you perform the test again. And recipe berpakan. Okay lah, this one okay lah. Okay, so using double log model, it helps to remedy the problem. So this is using log. If let's say the original one just now we have LE, income, C income, and excess. So another option is using the upper standard error, originally or second, but you also can, because this one we have 80 something, so maybe okay lah, not that okay lah, maybe we can try to use this one lah, the Hero White. Okay, to get more reliable estimate. But the problem with this one I mentioned before, we don't have any way to check whether the problem solved or not. So we can only trust us, meaning that you have to make sure your data is large enough. Okay, so I think you refer to the textbook, main textbook. I think this one. I mean, that's one of the textbook. So it gives an example of the use of this method of standard error for the case of sample size 45 mistaken. So, but you have to remember, I mean, it's not always able to overcome or to reduce or to remedy the problem. So I mentioned, so my suggestion is that don't try not to use this one, standard error if the sample not that large. Okay, not that large. So 85 maybe to some extent is able to help to lessen, but whether it solve the problem totally, I'm not that sure. Okay. Okay, so alright, I think that's all right. So that's all. See you again next 2 weeks. So next week we won't have lecture.